Hello everyone, Assalamu alaikum. Today we're going to talk about a project which name is a Topology Independent TDMA based MAC protocol for vehicular networks. My name is Rifatuzzaman Turjo and my partner name is SAMIUR Rahman. This is the contents of our project that we did. Now I'm going to talk about what is TDMA. TDMA is a time division multiple access. It is a channel access method for shared medium networks, and we use TDMA because it separates users according to time. It ensures that there will be no interference from simultaneous transmissions and is the most cost-effective technology to convert an analog system to digital. Now I'm going to talk about what is MAC address and how it's related to our project. MAC address is used to ensure the physical address of a computer. It uniquely identifies the devices on a network. In our paper, we propose a topology independent MAC protocol for vehicular networks in which the time slots to the vehicles are not assigned statically but calculated by the vehicles themselves in a conflict-free manner using their current position on the road. Now we talk about what is RSU. What is RSU? RSU uses DSRC communication. By DSRC, I meant dedicated short range communication, which is a one-way or two-way short range to medium-range wireless communication channels specifically designed for automotive use, and a corresponding set of protocols and standards. A special wireless communicating device located on the roadside that provides connectivity and information support to passing vehicles, including safety warnings and traffic information. The structure of time frame, the duration of time slots, and the time synchronization among the vehicles is supported through the roadside units (RSU) by transmitting a special message called beacon periodically. In the next slide, I will describe what is beacon and how does it work. Beacons are small wireless transmitters that use low energy Bluetooth technology to send signals to other smart devices nearby. They are one of the latest developments in location technology and proximity marketing. Put simply, they connect and transmit information to smart devices. And how does it work? The beacon device itself is incredibly simple. Each device contains a CPU, radio, and batteries, and it works by repeatedly broadcasting out an identifier. This identifier is picked up by your device, usually a mobile, and marks out an important place in your environment. The identifier is an is a unique ID number that your smartphone recognizes as unique to the beacon. Once connected, the beacon will carry out whatever function it has been programmed to perform. Example, the lights of a runway is an example of beacon as it provides direction and guidance to the airplane. Now I'm going to talk about the literature review. For our project, we reviewed basic concept of networks, introduction to protocol layering, and network models. From our course, Common Networks by itself, and the topics we also covered division multiple access from the previous courses as we did in the Communication Engineering 1 and Engineering 2. We also studied our original paper, which is obviously called a Topology Independent TDMA based MAC protocol for vehicular networks. Now I'm going to talk about the motivation of our project. The motivation to this project as this removes the requirement for the vehicles to have an explicit clock synchronization mechanism. The proposed MAC is topology independent in the sense that it doesn't require rescheduling of time slots due to vehicle movements. As we map the road segments to the time slots instead of vehicles, finally, the proposed TDMA do not suffer from the problem of interference between vehicles managed by adjacent RSUs, as there is no overlap between the areas covered by adjacent RSUs. It reduces the message overhead significantly. The solution proposes to logically divide the road structure into segments and establish a one-to-one mapping between the segments and the time slots.
Now I'm going to explain why TDMA-based MAC protocol address is important for vehicular networks. In general, as we could say that the TDMA-based MAC protocols for vehicular networks are either distributed or centralized, and both the types uh, convey a big message overhead in the dynamic network topology, as a fresh TDMA schedule has to be regularly calculated. Now, as you can see, the first point, in centralized scheme, the message overhead occurs due to the frequent transmission of TDMA schedule by the RSU, roadside units, whereas on the other hand, the distributed schemes, it occurs due to the exchange of protocol messages between the vehicles to decide their transmission slots. In order to solve this message problem, TDMA-based MAC protocol has been proposed for infrastructure-based vehicular networks, which is independent of network technology and hence minimizes the message overhead in a significant way. Uh, the solution gives a proposition to divide logically the road structure into segments and make an establishment of a one-to-one mapping between the segments and the time slots. A vehicle can transmit in a time slot mapped to the segment in which the vehicle is recently located. Uh, as you know that the vehicles receive the logical partitioning information of the road, uh, the distance of the length of the time slot and the number of time slots in the time frame from a special message called beacon, which is already explained in the beginning of this presentation. This beacon is transmitted by RSU in a periodic way. These beacon messages assist the vehicles to make the synchronization with the RSU, which is needed to relocate the correct time slot and then prevent the collisions from happening. Thus, this removes the requirement for the vehicle to have an explicit clock synchronization mechanism. As you can see that this does not require any rescheduling of time slots. This is because of the vehicle movements. The road segments have been mapped to the time slots instead of vehicles, as mentioned before. Finally, TI-MAC, which is Topology Independent MAC, do not suffer from the problem of interference between vehicles managed by RSUs, as no overlap has been occurred between areas covered by adjacent RSUs. Now I'm going to move on to I'm going to move on to the Topology Independent MAC, which is TI-MAC for short. Now I just want to say that a star topology-based vehicular network has been considered as it consists of a single RSU. Further, these vehicles are assumed to be moving, as you could see here in this diagram, that they're assumed to be moving along a straight road infrastructure. The transmission range of RSU is considered greater than the transmission range of the vehicle. This is because of the asymmetric transmission range between roadside unit and vehicles. The nature of communication from RSU to vehicles become single hop from RSU to vehicles, and then multi-hop if you consider the reverse from vehicle to RSU. The time, then you could see the timeline into multiple MAC superframes, which means that the timeline is divided into multiple MAC superframes, and each MAC superframe consists of a beacon frame, CAP, which is contention access period, then CFP, which is contention free period. As this topic mainly deals with contention access period frequently, I'm gonna explain more about the contention access period. The CAP, which is in short, can also be used for RSU to vehicle communication whenever RSU requires to uh, deliver some command to the targeted vehicles. Uh, in order to make it simple, it's been assumed that CAP is not present in the MAC superframe while performing erratic calculations. When the CAP is present, its length can be added as the offset uh, in an appropriate manner in all the calculations. The duration of a time slot in the MAC superframe can be calculated in as slot size, which you're seeing the equation right now. Slot size equals D by B. Here, the D is the size of the frame to be transmitted, and B is the available bandwidth. And now I'm gonna explain the diagram here. Uh, as you can see that there's a beacon frame on the left, then there's a contention axis period, which has 4 slots inside it, and then contention free period, which has 15 slides followed by again beacon frame, and each one is a time slot, and each time slot consists of a road segment. So the MAC superframe is established by RSU, and time domain defines uh, a framing which is logic of the road superframe, where each road superframe consists of the same number of segments as the number of time slots present in the superframe, as mentioned when I try to explain the diagram. The size of the segment, which is SEG, size in short, is decided by the RSU and communicated to the vehicles through beacon message. The seg size is a design parameter, and the RSU decides its value based on various parameters such as the mean wavelength of moving vehicles, followed by current vehicle density, and the accuracy of the GPS receiver, which is now available at the vehicles, and the delay requirement of the given application is already there. Well, in that matter, the density of the vehicle is extremely low. This can be increased from the segment size to decrease the mean transmission delay, but the increase in seg size also makes the probability increase of more than 1 or 2 vehicles present in the segment, and this leads to the collision of the frame. You know, let me give you an example of a car driving on 2 sides of the road. Suddenly the car on one end meets a truck on the other end, and meets face to face, and then collide with each other. Then the accident happens. So here it says that the RSU chooses an optimal segment size that gives the lowest average transmission delay corresponding to a particular density. Now I'm going to explain the equations a bit. The number of TDMA slots present in the contention-free period portion is selected as if we are avoiding some hidden terminal problem in the network by making the division of twice the range of vehicle to vehicle, which is V2V in short, vehicle to vehicle communication with the seg size. Now here you see that the DV is V2V communication range. The value of n slots can be calculated as n slots equals to 2 into dv divided by seg size, as mentioned before what seg size is. Keep in mind that the number of segments in the road superframe is the same as uh, MAC super frame. The vehicles at distance, uh, which is more than the end slots multiplied by the set size meters, can make a simultaneous transmission at a time slot without making any collision. To calculate the ID of the segment within a road super frame based on the current location of the vehicle has to know the coordinate of the location from where the area covered by the roadside units on road starts, which we say uh, init core. In short, using the information present in the beacon frame received from the RSU, the vehicles present in the RSU range can calculate their segment ID on the road super frame. They can transmit the frames. The value of segment ID is calculated as segment ID, uh, which is equals to current position minus the uh, area covered by the RSU on road starts, which is init core in short again, then size of the segment, and then number of slots. As soon as the slot ID in the current MAC, uh, resembles with the current SCG of the vehicle, the transmission starts in the data frame. In case more than one vehicles being present in the segment, the vehicles are going to transmit with a probability of 1 divided by n, where n is the number of vehicles present in that particular time slot. However, henceforth, uh, it's seen that the optimal choice of set size can minimize the probability of such situation. On the other hand, there's a choice to uh, make a solution for the contention in that situation in order to give the priority of the vehicle with current position, which is greater than any other vehicles present in the segment. Your part, man.
Now I'm going to talk about the results that we found in our project. In figure 3.a, it shows the average access delay performance of topology independent MAC protocol with respect to the varying segment size. A packet is generated at each vehicle after every 400 milliseconds. Initially, access delay decreases from segment size 1 and 2, 1 to 2. This is because the probability of more than one vehicle in a segment is higher for larger segment sizes. In figure 3.b, where the packet drop rate starts increasing after the optimal segment sizes corresponds to a particular vehicle density. At one extreme, when the vehicle density is very less, for example, in case of highways, a very low access delay as well as packet drop rates can be achieved by keeping a very large segment size. In figure 3.c, as we can see, it shows the effect of network traffic load on access delay. At certain amount of load, it starts increasing exponentially because the rate at which a vehicle gets the packet from higher layer to transmit becomes higher than the rate at which it gets the time slots. And the load point at which the system becomes unstable comes earlier in case of higher vehicle density due to packet collisions.
Now the conclusion part. As mentioned earlier, that this is a proposed topology independent TDMA based MAC protocol for infrastructure based vehicular networks, by which vehicles have the independence to calculate their transmission time slots simply uh, uh, depending on their, based on their recent position instead of being communicated uh, by a unit which is centralized, such as roadside unit, or by running a scheduling algorithm which is a distributed one among themselves. Uh, this this part uh, removes the overhead involved in the TDMA scheduling, and this makes the protocol highly dynamic. Um, in future, if the evaluation uh, about the actual performance of the planned idea occurs, then there's a further plan to there's a further plan for extension of the protocol for networks uh, with more than one RSU, hence which is actually the multiple RSUs, and also to perform uh, the exact the exact modeling of available GPS with the vehicle and the network generated by the vehicles, as well as the vehicle mobility. We hope that uh, uh, this makes the vehicle users easier to use the use the GPS track, as well as this uh, TI-MAC in order to prevent collision in the future, and so on. And this is it for our presentation. Thank you so much.